Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and today in 20 minutes rapid revision video I am going to discuss a very important chapter, moving charges and magnetism. In your PUC this chapter weightage is around 11, and if you practice this chapter you are going to get at least 11 marks common. So without any delay, let us start with the rapid revision. And if you are watching this channel for the first time, or if you are someone who is just watching but not subscribed to our channel, don't forget to subscribe. Subscriptions is very important for our channel to grow, and we will bring out more and more videos for all of you if our subscriber goes up, right? So that is the deal. Don't forget to subscribe, and we will start with the chapter. And as usual, we will look into the concepts that we are going to discuss. This is slightly lengthy chapter. So Lorentz force, force on a current carrying conductor, motion of a charge in magnetic field, Biot-Savart's law and Ampere's law, solenoid, galvanometer and their conversion. So these are all the concepts, including this is not the limited, all the concepts of this chapter we will be discussing, but these are the highlights of this chapter. Now let's move on with our first concept, Lorentz force. So what is Lorentz force? Lorentz force is basically when you are Lorenzing something and you are getting some force, then it is called Lorentz force. No? Okay. So basically when you are keeping a charged particle, when a charged particle is moving in an electric field and magnetic field, a charged particle, say Q, is moving with some velocity, okay, in a electric field as well as some magnetic field, okay. They may be perpendicular, they can be in any direction, does not matter, okay. So as long as the particle is moving, there is an electric field, there is a magnetic field, then this charged particle Q will experience two different forces. One force is due to the electric field, which is static, obviously Q into E, and there is a dynamic force based on the velocity angle between them, and that is called magnetic force, okay, QVB sin theta. Okay, so those two forces combined are known as Lorentz force. So if you take the expression of electric force Q into E, and because force is a vector quantity, we are writing in vector form. Force due to magnetic field is Q V cross B, and the entire force is given by F is equal to Q into E V cross B. So this is the Lorentz force. Only the magnitude of this magnetic force is given by Q VB sin theta. Okay, if theta is 90 degrees, then sin theta becomes 1. Okay, so this formula is also important. Now let's move on. Force on a negative charge is opposite to that of the positive charge. So the formula that we have used, where we have assumed Q is positive, there is no sign involved, that means Q is positive. Now if you find the direction, you calculated everything for a positive charge, but in the question it is mentioned a negative charge, then what to do? So you should remember that for a negative charge the force will be in the opposite direction. So QVB minus QVB, Q into E minus Q into E. Okay, so the direction of force on a negative charge is in the opposite direction. The vector product makes the force due to magnetic field vanish if velocity and magnetic field are parallel or anti-parallel. So QVB sin theta, so the force will be 0 if theta is equals to 0 or theta equals to 180 degrees. As simple as that. So if velocity vector and magnetic field vector, they are in the same direction, or velocity vector is in the opposite direction, so that they are parallel or anti-parallel, then the force acting on the charge is 0. The magnetic force is 0 if the charge is not moving, that is the magnitude of velocity is 0. If the charge particle is static, then also the force is 0. So this is a very common topic for MCQ questions. A strong magnetic field is applied across a point charge, a static charge. What is the force acting on this charge? 0, because charge is at rest. Only a moving charge feels the magnetic force. And if you want to practice more such MCQs, then ABHYAS KCET test series is here, where you will be preparing for KCET exam, KCET 2026 exam, and here we are going to give you 35 KCET level papers. That means you are not only preparing what type of questions is going to come in KCET, how to approach a question in KCET, the level of difficulty is also the same as KCET, so that you are aware that how many difficult questions will come, how many easy questions will come. That preparation is happening. Not only that, you are also getting real KCET exam pattern and timing. That means you have to answer those questions within a given time interval. That means you will be sure when you finish this test series, you will be sure, okay, how many questions I am able to answer in this 60 minutes time. So that will give you a confidence. Okay, I am able to solve all 60 questions, means I am in a good state. So that is what is very, very important for all of you to practice the time management. And if you practice the time management, you can score a very good rank like Prajwal, Kiran, Deeksha, Sachin and Mohammad Sahil. Okay, so they all had purchased ABHYAS KCET test series, and this year we are going to give you absolutely free of cost chapter wise 10 years KCET PYQs. Okay, so you will be getting those as a form of quiz. You can practice previous year questions as a form of quiz, so you will know that how many questions of the previous year paper you are able to solve them without looking at them. Okay, and everything is priced only for 1499, and those who are PCM student, those who are biosciences student, everyone can get this test series for 1499 only. Okay, now let's continue with our discussion. Motion of a charged particle in a magnetic field. Now if you want to purchase ABHYAS, link is given in the description, right? Motion of a charged particle in a magnetic field. A charge moving in a uniform magnetic field will experience a force. Okay, so if the charged particle is moving in a uniform magnetic field, it will experience as a force. So motion and magnetic field obviously gives rise to the force. This force acts as centripetal force and produces a circular motion perpendicular to the magnetic field. Here theta is 90 degrees, so sin theta is 1. So QVB is the force, and that force, because velocity and magnetic field are perpendicular to each other, okay, the force is very special. The resultant force actually supplies the required centripetal force for the charged particle to move in a circular motion. So if you see over here, the velocity is in this direction, the magnetic field is into the page of the paper. So velocity and magnetic field, they are in perpendicular direction. So because they are perpendicular, what happens is that the force that acts on this particle, that acts on towards the center, and because of that centripetal force, the particle starts rotating in a circular motion. And in this case, everything is very, very important. The velocity, the angular velocity, the frequency, the time period, the radius, etc. are important quantity. If velocity has a component along V, so now the velocity is not exactly perpendicular, but it has a parallel component along with V, so the angle is not exactly 90 degrees. So if the angle is between 0 and 90, then what will happen? At 0 degree angle, force is 0. At 90 degree angle, it is rotating in a circular path. But if the angle is between 0 and 90, then what happens is that the particle will undergo helical motion. Helix. Okay, the motion looks like this. The shape of this is called helix, and this motion is called helical motion. So as if the charged particle is moving in a perimeter of a spring. Okay, this is like a spring, right? So the charged particle is moving along the perimeter of a spring, right? So here there is a parallel component along with V, so this does not experience any force. This will move, this will take the particle in this direction, but there is a perpendicular component which is trying to move in a circular motion. So both motions are actually happening, linear motion as well as a circular motion, and that's why the ultimate motion is a helical motion called this is a very important point for MCQ questions. If the angle is between 0 and 90, what is the shape of the path? Path is a helix. The path is a helix. The motion is helical motion. Now, as I mentioned, the radius, angular velocity, time period, they are all very important. So, radius of circular path is given by mv by qb. I have done this derivation. You can check in Brahmastra series as well as in our master stroke. There I have done it. Angular frequency is given by qb by m. And normal frequency, angular frequency or angular velocity, both are same quantity. Normal frequency is 2 pi omega. So if you put the value 2 pi qb by m, okay, so that will give you the frequency, and time period is 2 pi by omega, so it will be 2 pi m by qb. Okay, so you can calculate everything. Sorry, I make small mistake. It is not 2 pi omega, it is omega by 2 pi. Okay, omega is equal to 2 pi f. So frequency can be calculated from here, qb by 2 pi m, and time period is 2 pi m by qb. So as you can see, angular velocity is independent of the velocity of the particle. So here there is no velocity term, but radius of the motion is dependent on velocity. Okay, so angular velocity or frequency both are not dependent on the velocity of the particle. It depends only on the charge and the magnetic field. Let's move on to the Biot-Savart's law. Biot-Savart's law is basically a law where you are trying to find magnetic field at a distance from a current carrying wire. So suppose there is a current carrying wire, you are trying to find magnetic field at a distance p, at a distance small r, at a point p from the current carrying wire. Then the magnetic field produced by a small current element, because the wire is not uniform, you have to take an element, and the magnetic field due to this small element is basically given by dBp is proportional to current I. dBp is proportional to the length of the element, so bigger the element, more magnetic field it will produce. Okay, and it is inversely proportional to the square of the distance. So this is the same as Coulomb's law, right? And dBp is also proportional to sine theta. So combining everything, we get dBp is I dl sine theta by r square. Okay, and in terms of vector notation, this can be written as dBp vector is given by mu naught by 4 pi I dl vector. This is slightly different, that's why I am telling you r vector divided by r cube. So if you see that here is r square, here is r cube. Why, sir? Why there is a difference? The main difference is because we have multiplied by r vector. We have multiplied by r vector. So one r magnitude wise is more in the numerator than in the denominator. That's why we have r cube over here. But if you take the scalar form, r will cancel, one of the r will cancel, and you get r square. So this is the scalar form, this is the vector form. Vector form is also important for your PU preparation, because they ask write Biot-Savart's law in its vector notation and explain the terms. So you don't need to explain everything, you just need to write this, and you get the you mention what is dBp, what is this, the diagram is compulsory, and everything else, mentioning everything is also very, very important. Now remember that in vector notation sine theta is not there, because cross product is there. Cross product will give you a sine theta when you convert it into scalar form. Okay, mu naught by 4 pi is called permeability of free space, and its value is 10 to the power of minus 7 Tesla meter per ampere. Now from here mu naught can be calculated. Mu naught is 4 pi into 10 to the power of minus 7. Clear? Now magnetic field versus electric field, both are long range and depends inversely on the square of the distance. So magnetic field and electric field, obviously there will be a comparison between them. The principle of superposition applies to both of them. The electric field, electrostatic field is produced by a scalar source, namely an electric charge. Okay, the magnetic field is produced by a vector source called I into dl. Okay, so electric field and magnetic field, even though they are very closely related, one is produced by an electric field, one is produced by a scalar source, one is produced by a vector source. Even though both of them are vectors, there is a possibility that a vector can be produced by a scalar. Okay, the example is electric field. Electric field can be produced by a static charge. Charge is a scalar quantity, we know, but in this case magnetic field is produced by the vector quantity, which is called current element. Current element is given by I into dl, the same dl that we have used in the last case. The electrostatic field is along the displacement vector joining the source and the field point. The magnetic field is perpendicular to the plane containing the displacement vector and the current element IDL. Okay, so basically electric field, if you try to find electric field due to a point charge, it is basically line joining the point and the charge. But where you are trying to find the electric field due to a current carrying wire, electric field will be perpendicular to both this current carrying wire and this distance. Okay, it is basically perpendicular to both of them. Okay, so straight current carrying wire, magnetic field is into the page of the paper. Okay, so magnetic field is perpendicular to both of them. Electric field is just a line joining the point and the starting point. So that is the major difference. Now there is an angle dependence of the Biot-Savart's law which is not present in the electrostatic case. Electrostatic case E is kq by r square, so there is no angle, but in case of Biot-Savart's law there is an angle sin theta which is coming from the cross product, because of the obviously the fact that magnetic field is perpendicular to both of the radius vector as well as the current carrying element. Now magnetic field due to a straight conductor, if the conductor is straight, magnetic field due to a straight conductor carrying current is basically given by this formula, and it is into the page of the paper. Okay, into the page of the paper is given by this symbol. If you are trying to find magnetic field on this side, then it will be out of the page of the paper. Out of the page of the paper is given by a dot symbol. Okay, dot means out of the page and cross means into the page. Okay, and its simple formula is mu naught by 2 pi I divided by r. So for a straight current carrying wire, magnetic field is proportional to 1 upon r. Okay, there is no r square in dependability, it is proportional to 1 by r. So that is also can be asked. Circular current loop, this is the derivation is very important. The derivation again I have done in my lecture in Brahmastra, you can go and check that out. So here we have a current carrying wire and we are trying to find magnetic field at a distance r. Current carrying wire is say carrying a current I. The radius is given by r. Then the magnetic field at a distance b is actually along the x direction only, so this is bx. Magnetic field exists only along the direction of the axis. There is no component in the perpendicular direction, no component in this particular direction. Okay, so magnetic field in this direction is 0. Now that magnetic field is given by mu naught I r square divided by 2x square plus r square into the power of 3 by 2. Obviously the value looks little complicated. If you take the magnetic field at the center, it is a constant, it is mu naught I by 2r. Okay, for x very greater than r, that comes to a that gives you a very interesting value. Magnetic field is given by mu naught by 4 pi 2m by x cube, which is similar to that of the electric field due to a dipole on its axis. So if you remember, electric field due to a dipole on its axis was given by 1 by 4 pi epsilon naught 2p divided by r cube. Okay, so instead of r here we are using x. Obviously the distance is measured by x. Instead of p we have m, but this is the electrostatic constant, this is the magnetic constant. So this is very comparable to electric field due to a dipole on its axis. So you can say that this current carrying loop is behaving like a magnetic dipole. Okay, where magnetic moment is given by I into a for n number of turns NIA. Okay, NIA is the magnetic dipole moment for a current carrying loop. Now Ampere's circuital law says that the magnetic field around a closed loop depends only on the electric current passing through the loop. Suppose we have a closed loop and some current is being passed through that loop. Okay, so only if you take the line integration of this closed line integration of magnetic field along this line, and if you add them, then B dot dl gives you mu naught I. Okay, the current that is only enclosed current, it does not matter if there is a current in this direction, some current in the opposite direction. Okay, if any current is outside, we will not consider it. Any current inside, you have to take the addition based on their direction. Okay, so this is similar to that of Gauss's law. In Gauss's law it was a static charge. In case of Ampere's law it is a moving current carrying wire. Okay, now solenoid, previously it was you have to find the magnetic field using Ampere's law, but that derivation is no longer part of the syllabus. But magnetic field inside a solenoid can be calculated using Ampere's law, and that is given by mu naught n into I. Okay, n is number of turns per unit length. That is very important. It is not total number of turns, it is number of turns per unit length, and that is given by mu naught n I. Simple formula, very easy. Now force on a current carrying wire. So if you are keeping a current carrying wire in an external magnetic field, that current carrying wire experiences a force. Okay, the current carrying wire experiences a force. That force is given by I into L cross B, and scalar form is BIL sin theta. Okay, BIL sin theta is the force that is acting on the current carrying wire. Force between two parallel currents, force between two parallel current. So when we are having two parallel currents in same direction or in opposite direction, there is a force between them, and the general formula for this is mu naught n Ia Ib by d into L. Again, the derivation I have done in Brahmastra. And if you say the force between this one is F12 and this is say F21, then by Newton's third law of motion, this force has to be equal and opposite. Now parallel currents, when they are in the same direction, they attract, and if the current is in the opposite direction, then they repel each other. Okay, this is also very, very important for MCQ questions. Parallel currents attract each other, opposite currents repel each other. Okay, the ampere, from here you can even define the ampere. First of all, you have to convert it into force per unit length. So force per unit length is given by mu naught n Ia Ib by d, and there is no L. Okay, so force per unit length means the L is basically divided. It is let me write in short. So F divided by L gives you the force per unit length. Okay, now when two very long straight parallel conductors, each of the negligible cross section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 into 10 to the power minus 7 Newton per meter of length. So if 1 ampere current is being allowed through two parallel wires kept at a distance of 1 meter distance, then the force acting between them is given by this value. Very negligible force, but still it can be measured, and this is an electrical definition of ampere. Now let's move on to torque on a rectangular current loop. Suppose we have a current carrying loop, and when it is kept inside a magnetic field, because we know that individually both of them will experience forces based on the BIL sin theta formula, there will be a torque acting on each of them, and the torque is given by Ia into B. Okay, that derivation can be done. If you want me to do this derivation, I can do it. Let me know in the comment section below. So torque is given by Ia into B, and torque is given by A cross B. The magnetic moment of a single loop is defined as M equals to I into A, or for n number of turns it is NIA, and the torque is given by M into B. Okay. Now moving coil galvanometer, there is one more fact that you can do, that if you put everything, you get scalar form of torque is BINA. Okay, you can remember this. Torque acting on a current carrying loop in a magnetic field is BINA. Okay, I used to remember it in different form. One of my students says you can remember it like this. So BINA is the torque that is acting on a current carrying loop. Now let's move on. Moving coil galvanometer. Moving coil galvanometer basically is application of the torque acting on a current carrying loop. So if you apply a current carrying loop in a magnetic field, then it experiences a torque, and if you can somehow measure that torque, then you will be able to find the amount of current. So that is a part of the calibration of the galvanometer. So when you have calibrated the galvanometer, okay, based on the current, it deflects different amount. Okay, and angle of deflection phi is directly proportional to the current, and that galvanometer constant is given by NAB divided by spring constant. Okay, detailed explanation if you want, you can check my master stroke. Galvanometer constant is called G. Now galvanometer to ammeter conversion. An ideal ammeter should have a zero resistance. In practical, ammeters of the resistance kept as low as possible. Convert a galvanometer into an ammeter, we need to connect a shunt of a very low value resistance parallel to the galvanometer, so that most current passes through the shunt and very small amount of current passes through the galvanometer. Okay, this will protect the galvanometer, as well as it will allow the overall resistance of the galvanometer to low down, and the current that you are measuring is given by I equals to Ig. Ig is the galvanometer current, G plus S divided by S. G is the galvanometer's resistance, S is the shunt resistance. The current sensitivity is given by this value NAB by K. Current sensitivities can be increased by increasing the number of turns present in the galvanometer. Now galvanometer to voltmeter. Galvanometer to voltmeter, ideal voltmeter should have an infinite resistance, but we cannot have an infinite resistance which can measure current voltage. So that's why we use something which has a very high resistance, and for that we use a series resistance along with the galvanometer to increase its resistance, and thus it will be helpful to measure voltage. Okay, now the voltage sensitivity is given by this. Now voltage sensitivity cannot be increased by number of turns because N by R is fixed. Okay, here we have a resistance, so this resistance actually decreases the effect of number of turns. Now if you increase the number of turns, resistance will also increase proportionally so that their ratio remains same. The voltage that you are measuring is given by Ig into G plus R. So this is the end of this lecture. If you have any questions, any comments, and if you want me to explain any other parts, don't forget to mention that in the comment section below. Also join the WhatsApp community by clicking on the description, read more. Second link is joining our WhatsApp community, and there you will get all the PDFs of this lecture and all the lectures that we are doing in our channel. And if you want to purchase ABHYAS, the link is also there in the description. I will be back with a new chapter very soon. Till then, bye.